increasing. As the X values increase, your Y values are also increasing. That's what we mean about increasing intervals. When we talk about decreasing, where is the function decreasing? As the X values increase, the Y values are decreasing. So we always read these graphs from left to right. So that is what I'm referring to. You'll notice I have two different color graphs here, one in red, one in blue. So if that is my definition of increasing and decreasing, and you'll notice the red graph is our original cubic function. And the derivative of a cubic function, remember, because we're subtracting 1 from the highest degree, we have a quadratic function. So in blue, we have the derivative function. So original function and then the derivative function. So in this lesson, we're going to try to figure out and observe different types of examples and different types of graphs and see what conclusions we can come from them. So over which value is f of x increasing? Well, we can see as we said, as our x values increase, the y values are decreasing. So when x is less than 3, and when x is greater than 1, if we're looking at that number line, we can see that f of x, our red graph, is increasing, right? And we're not when we're reading the graph from right to left, but we're reading the graph from left to right. As the x values increase, the y values are increasing. But the graph in between that interval, so in between -3 and +1, from this point to this point, our graph of f of x is decreasing. So what can we say, what is true about the derivative function when f of x is increasing? So this is when we're comparing the intervals when x is less than 3 and x is greater than 1. And when we look at the derivative function, and we have to color in the derivative function, we'll notice in the intervals where f of x is increasing that the derivative function is always above the x-axis. Above the x-axis when f of x is increasing. That's a key component of what you need to know for the Module 3 test. When f of x is increasing, the derivative function is above the x-axis. So that means the opposite happens when f of x is decreasing. When f of x is decreasing, we can expect that our derivative function is going to always be below the x-axis. And we're going to test different functions to see whether this is true. But something I'm going to include in your notes, and this is something you would want on your study notes. So I've summarized what it means to be increasing or decreasing in general, but the effects of f prime of x on f of x. So when the graph of the derivative function is positive or above the x-axis on an interval, then we can, so we're doing the opposite. If we were given the derivative function and we had to determine or make conclusions about the original function, we know that the original function is increasing over the interval. Similarly, when the graph of the derivative function is negative or below the x-axis, we know that the function decreases over that interval, right? So this is a test on curve sketching. We need to, in order to be able to sketch curves without, figuring out all the roots and everything, this is some basic knowledge you should have for curve sketching. And this summarizes a key component of a rule for the test. Now, regular Mary Ward we would be doing lots and lots of sketching on the test. Here, not as possible. So we have to figure out, is this still going to be a test that has much more multiple choice questions and a few components where you have lots of time to graph. Okay, now when we talk about a critical number, it's a value of A in the domain where the derivative is equal to 0 or, and the or is big, or the derivative does not exist. This is what we call critical numbers. And this can yield different or look different in different examples. So when I talk about a local maximum, so remember, f of x is the original function. So if I have a local maximum here, that doesn't need to be the maximum for the entire graph. A graph can have multiple little maximum points, and that's what we call a local maximum or a local minimum. So if that is happening in the original function, then you'll notice that the derivative is equal to 0. In other words, it crosses the x-axis. We have a root at that point. And we know with the local max or local minimum, the derivative function is going to change because it's at the x-axis. It's going to be changed from being above the x-axis to below the x-axis, or below the x-axis to above the x-axis. That always happens when we have a local maximum point or a local minimum point. Now, in the case that we have neither, so something that looks like this, not a maximum, it's not a minimum. Now, at that point, f prime of x is still equal to 0, but the difference here is it does not change signs. It does not go from above the x-axis to below the x-axis. It can stay from above to above or below to below. And we're going to explore that a little bit further in these modules. Now, a big thing to remember is when you have a cusp, a sharp cusp in the original graph. So a sharp cusp. This is a situation where the derivative does not exist, but still changes. So you'll notice we have an asymptote in this particular example, but we still move from the graph as we read this graph from left to right, that the left part of the graph before this cusp happens, or this asymptote happens, the derivative was below the x-axis. And then we move to the situation that to the right of the asymptote, the derivative is above the x-axis. Okay, so this table is key to include in your study notes. So a conclusion that we can draw is that local maximum or minimum points when the sign of the derivative changes. If the sign of the derivative does not change, so that means we're staying above the x-axis or staying below the x-axis, you do not have a local max or local min. Okay. So something else we can say about critical numbers of a function is a value of a in the domain of the function where the derivative is equal to 0, it does not exist. We've already explored that. Critical points could be local extrema, local maximum, or local min, but that is not necessary. However, you must test around the critical point. Don't just assume and take the critical point at face value. You want to test certain points around the critical points. You're going to see this a lot in your unit guide for unit 12 to see if the derivative changes signs. This is called the first derivative test. First derivative test is key because we can also move on to the second derivative test, which we're going to explore next week. So we have to make sure we get it right with the first derivative test in order for every other part, sequential part of the question to make sense. In regular Mary Ward, a test like this has very few questions, but each question is worth lots of marks because there's so many stages to the question. Factoring, then finding the critical numbers, critical points, putting in charts, testing. So I'm going to walk you through a beginner question. So we're going to practice using critical numbers, and I'm going to show you the first derivative test. So we have to obviously start off with the function. Okay. After we write down the function, we have to take the derivative of the function. So we know this. Sometimes the derivative is going to require the product rule, the quotient rule, the chain rule in conjunction with the power rule, product rule, quotient rule. There's a reason why we're not teaching curve sketching before module 2. You have to know how to calculate derivatives in order to move further in this course. So in this case, it's very easy power rule application. Derivative is 6x squared minus 18x minus 24. Now I have to simplify this function by setting it equal to 0 and trying to find my critical numbers, what you might interpret as the x-intercepts. So 6, 18, 24. I know that has a greatest common factor. So I'm going to take the greatest common factor out so that I have positive 6 over here. Take it out, and now I have x squared minus 3x minus 4. You can use a number of different strategies, but that is very simple to factor. So once we factor that, I know that I have my two x-intercepts when x is equal to positive 4, x is equal to negative 1. Two possible critical numbers. Now, the reason we have to call them critical numbers, they're just the x values. So in order to get the critical points, I have to substitute those x values into my function. Right? So if I plug in x is equal to 4, notice I'm not substituting it into my derivative function. I'm substituting into my original function. The derivative helps us find the critical points. You're not finding the x-intercepts of the original function. The derivative finds the critical points, the critical numbers. We use these critical numbers to plug into the original function to find the critical points. So when x is equal to 4, the corresponding y value is negative 122. That is my first critical point, 4 and negative 122. My second critical point is when x is equal to negative 1, y is equal to positive 3. I would not get these values if I was factoring my original function. The first derivative test is key in order to get these critical points. So now that I have two significant points, what do I do with these points? What do I do with them? Well, I'm going to make a chart that illustrates my first derivative test. And I'm not going to just plug in these critical numbers, okay? What these critical numbers represent, and you can even plot them on Desmos, plot them on graphs, they're actually going to represent local max and local min. But we have to be able to test around those critical points, and I think we visited that a little bit in the functions course, to figure out how to truly sketch this graph. So my critical points, I'm going to just scroll down a little bit. Negative 1, so the first thing I want you to write down, at negative 1, I have a local maximum. At negative 1, 3, my first critical point. At x is equal to 4, I have a local minimum, right? And besides those critical points, on the left, I have negative infinity. On the right, I have positive infinity. That's where I'm going to start. I know I have a local max and a local min, and I have these potential test values. Now we're going to do a lot more charts like this in module 3, but after this example, I'm going to focus more on looking at different graphs and really analyzing them, because today is meant to be just an introduction lesson and really hammering in the concept of increasing and decreasing intervals. Next time I have you in class, we're going to really focus on maximum and minimum points in length. But anyway, I'm going to choose arbitrary points. So Matthew's point can be different from Renee's point that you choose. It can be any point within these intervals. So within negative infinity and -1, I could even have chosen negative 100, right? Anything in that interval. In the interval -1 and 4, there's smaller numbers to choose from, but of course, I'm not going to choose a fraction. I'm just going to choose a simple number. I could have chosen a +1, +2. It really doesn't matter at this point. And then any number in the interval 4 and 5. I advise you to just pick a number that's close to your critical points, just to be as accurate as possible. But anyway, when I plug these values into the first derivative, this is why it's called the first derivative test. When I plug this value into the first derivative, I'm not concerned about the actual number. I'm just concerned, is the answer going to be positive or negative? So when you plug in -2 into your first derivative equation, you're going to get a positive value. When I plug in 0 into my first derivative, I'm going to have a negative value. And when I plug in +5 into my first derivative equation, I'm going to get a positive value. That's great, easy to do, but what does that tell you? Well, we have to go back to the rule we learned before. If the first derivative is positive, that means we're going to be increasing, the graph is going to be increasing in that interval. When it's negative, it's decreasing in that interval because we're reaching a critical point here. So remember, we went from maybe above the x-axis or to below the x-axis, right? So that means we have to, because at these critical points, we're going to have a 0 in the derivative function. So to go back to our rules, that just means when you have a positive, negative, positive, positives result in increasing original graph, negatives result in decreasing negative graph. So we know, according to this, that the graph is going to be increasing when x is less than 1 all the way to negative infinity, and also when x is greater than 4. The only time this graph is going to be decreasing is in this interval, in between -1 and 4. So we can summarize what we've learned from this chart, what I just said, increasing and decreasing. And now that we know that, let's analyze the actual graphs and verify the derivative. So the graph of the original function and the graph of the derivative corresponds to this. When x is less than 1, when x is less than 1, the original function is, less than -1, the original function is increasing. We read it left to right. So many times I have students tell me, Miss, no, it's decreasing. No, we're reading the graph from left to right, not right to left. That is key. And the only time f of x is decreasing is in between -1 and 4. So our chart, our first derivative test, verifies what we can see on the graph using Desmos or a graphing calculator. Okay, so at this point, we're just going to compare different graphs and their derivative function. And we're just going to talk about them like we would in a functions course. We're not going to do real charts. We're going to save that until our next lesson. So here we have a simple linear function, f of x, and we have a horizontal line as our f prime of x. This makes sense because the derivative of linear functions are always constant functions, right? So f prime of x is a constant function at y is equal to -2. Just by we're practicing looking at graphs and coming up with information. It's because a lot of multiple choice questions require you to think further and interpret what you're seeing or what you have in front of you in terms of an equation. So for each graph function, use the graph of f prime of x to sketch a possible function for f of x. Okay. Therefore, because our derivative is a constant function, f of x must be a linear function with a slope of -2. Because remember, the derivative is the slope, right? Derivative function requires a slope. So at y is equal to -2, it would make sense the linear function had a slope of -2. That's the only way we would be able to get a derivative of -2. And the y-intercept could be anywhere, right? There's many potential f of x functions for this, this f prime of x function. Okay. For the next graph, we have a linear function this time, and our original f of x is a quadratic function. So I know my derivative is a linear function. Therefore, f of x must be a quadratic equation, that function. That always comes from the power rule when we subtract 1 from the original function to get the derivative. And that's why we're going step by step from quadratic to linear to cubic to quadratic. You're going to see the progression in this lesson. So we know that f prime of x is greater than 0 when x is less than 2. Okay, so I'm going to say that again. The derivative, when x is less than 2, I can see that the derivative function is above the x-axis. So when x is less than 2, when x is greater than 2, I can see the derivative function is below the x-axis. So because of that, I know that f of x is increasing when x is less than 2 and decreasing when x is greater than 2, right? The derivative goes hand in hand with interpreting the behavior of the original function. Also notice that at this critical number, x is equal to 2, we're switching, f prime of x is switching from above the x-axis to below the x-axis, fitting what we know. And this also corresponds to the fact that we have a local maximum. Go over here. We have a local maximum at x is equal to 2. Okay, for this particular function, we have a local minimum over here. And so if we go back, we were talking about the local maximum of the original function. Here we have a local minimum of the derivative function that kind of corresponds to, it's not neither a local maximum or a minimum of the original f of x, but we know x is equal to 2 is going to be important in this function as well. So let's summarize. Our derivative is clearly a quadratic function, which makes sense because f of x is a cubic function. This is what cubic functions look like. When the derivative is above the x-axis, x is less than 2. So when the derivative is above the x-axis, x is less than 2, and x is greater than 2. So remember, because there's no clear local or maximum or minimum of the original function, our derivative function is not switching from above the x-axis to below the x-axis. It's staying above the x-axis. So we know that when you see a point like this, let me circle that. When you see a point like this on the original function where it's neither a local max or a local min, you expect your derivative to stay either above the x-axis or below the x-axis. So that's what I just said, that f prime of x does not switch signs on either side of x is equal to 2. Therefore, there's no local max or minimum at f of 2, but the tangent line would be horizontal at that point. If we were analyzing the tangent at the point x is equal to 2, because we have that type of behavior I circled in purple, our tangent line would be horizontal at that particular point. And virtual kids, if you have any questions, feel free to interrupt me at any point. Now, remember, the green function is always our f of x function. This is going to be a little bit more, not difficult, but interesting to analyze, because you'll notice if I take my highlighter, I have a local maximum as well as a local minimum. So I know that x is equal to 1 is going to be an important point, and x is equal to 5 as well is going to be an important point. So let's analyze the function. F prime of x is quadratic. Therefore, f of x has to be a cubic function, a little bit different cubic function than we saw before. You'll notice that once we get to the x to the power of 4 polynomials, those look more like a w. So we're sticking to cubic functions right now. When f prime of x is above the x-axis, we notice that happens when x is, if I take my highlighter in yellow, oops, when x is less than 1, so over here, but that is my original function, so I want to take that out. So f prime of x is above the x-axis when x is less than 1 and when x is greater than 5. And that corresponds to our increasing intervals when x is less than 1 and x is greater than 5. So what I've highlighted on the derivative function graph corresponds to the original increased function's increasing intervals. That is to be said that the derivative is below the x-axis in between 1 and 5. And you'll notice that in that interval, if I highlight that on the original function, we know that f of x is decreasing in that interval. So yet another example that sticks to our curve sketching rules. So we can see that at x is equal to 1 and x is equal to 5, my derivative function switches from above the x-axis to below the x-axis each time. So that's a clear indication that we have a maximum at x is equal to 1 and a local minimum at x is equal to 5, right? So when you need to justify why there's a local maximum and a local minimum, you can use the information in f prime of x to justify. Okay, so we are going to look at 2 more graphs before we go back to a chart and a possible application problem. So this is something that would be on a typical Mary Ward test. Sketch a continuous function for each set of conditions. So you would have had a blank grid paper here. The red is my actual answer. So if you were just given these conditions and you had to sketch a function with these conditions, well, what do we know from these conditions? F of x is increasing when x is less than 0 and decreasing when x is greater than 0. Well, how do we know that? Well, f of 0 is equal to, I know that the derivative function is above the x-axis when x is less than 0. The derivative function is above the x-axis when x is less than 0. So that means that when x is less than 0, this graph has to be increasing. And when the derivative function is below the x-axis, when x is greater than 0, that means when x is greater than 0, the function has to be decreasing. The only way for that to happen is that we need to have at x is equal to 4 a local maximum point. And that corresponds, so f of 0 is equal to 4, has to be a local maximum point. That corresponds to the fact that we are going to have a 0 probably with our derivative function or root for our derivative function at that point. So this quadratic function, reflected quadratic function, fits all the criteria that we were given, right? So the whole point of curve sketching, you're given a condition and you have to sketch a graph that meets those conditions based on the rules that you know about curve sketching. We can do another example like that. F, when the derivative is above the x-axis, when x is less than -1. Well, that means that our original function has to be increasing when x is less than -1. The derivative is above the x-axis again when x is greater than -2. That means our original function, sorry, not our derivative, but our original function has to be increasing again when x is greater than 2. F prime of x is less than 0 or below the x-axis in between the interval -1 and +2. That means our original function has to be decreasing in that interval. Therefore, we have to have a local maximum at x is equal to -1 and x is equal to +2 to justify what we know about the derivative function. Okay, so that's our last curve sketching example for today. I am going to leave an application problem for you to kind of analyze on your own, because of course there's going to be some word problems in the unit. I believe this is quite ironic. It is the temperature of a person with a certain strain of flu, not COVID, but with flu, can be approximated by this temperature function. It's a quadratic function, it has some fractions in it, where D is in between the range of 0 and 6. T represents the person's temperature in degrees per Celsius, and D is the number of days after the person first shows symptoms. So, perfect application with healthcare. During what interval will the person's temperature be increasing? So those of you who are looking at healthcare for your STEAM projects, this is a perfect example of how derivatives can be used. So from this original function, when we take our derivative, we're going to get a linear function. Okay, step by step, just like what I did last time. If I set this derivative function equal to 0, even with fractions, we can solve for D in order to get our critical number, right? Our critical number, not our root, but our critical number, because this number is going to be used to sketch out this function by plugging it into the original function. So when I plug in d is equal to 3 into my original function, and I also have the range between 0 and 6, right? We can't have, in this real life scenario, we're not talking about negative values in here. We're just talking about in between 0 and 6. And I know that d is equal to 3 is going to be a critical point. So I'm just looking at this range, 0, 6, with 3 as a critical number. I'm not plugging it into my y right now. I'm just using that range. Now, when I plug in any, T represents the person's temperature, and D is degrees Celsius. Or sorry, D is the number of days after the person first shows symptoms. So we can't have negative number of days. That's why we're starting our range at 0, right? So a day where the person first shows symptoms, maybe day 1. If I plug day 1 into my derivative function, I'm going to get a positive value. When I plug day 4 into my derivative function, if I got a positive value, that means the person's temperature is still increasing, right? So, but I'm getting a negative value here. That means I'm moving from an increasing function to a decreasing function. And so now I know exactly that a person's temperature will be increasing over the first 3 days only, and then decreasing after that. So clinical trials, equations come out of clinical trials, data comes out of clinical trials. And in order to find a correlation between the data, people have to come up with mathematical equations. That's why that right now in public health, there's so much data scientists and mathematicians being employed to figure out our curves and when things can open and reopen or close. It's based on data, clinical studies, mathematics. So they go hand in hand. So even though it might seem that, oh my gosh, my research for my STEAM project, it's really important to make these connections, to know that math and science do not work separately. They work together in so many different ways for real world applications.